Hello students, and welcome to another video. I'm Mr. Flynn. Today we're going to be discussing energy of reaction. We did two demonstrations, and there's video links here for you to access these same demonstrations. They're done in different classes. And one is an exothermic reaction, and one is endothermic reaction. And the one that we did first was the exothermic reaction. It's one that we've done earlier this year. We took sodium acetate trihydrate, and it's like a crystal form, like a white crystal. And what I did is I put it into a flask and I heated it up. And as I heated it up, it turned into a liquid. And as I slowly let it cool down, it turns into a supersaturated solution. And then what I did is I took some of that seed crystal and I dropped it into the flask, and it quickly turns into a solid, and it looks something like this. And when students felt it, after it was solid, it felt warm. It almost felt hot. And when heat is given off, it's an exothermic reaction. And we're going to talk today about why that is and how that occurs. The second reaction was an endothermic reaction. We were using ammonium nitrate and barium hydroxide, and I mixed them in a Erlenmeyer flask, and I jogged them around, and it got colder and colder, and I let students feel the bottom. In this video, the endothermic reaction, I believe he goes through and actually sticks it to a block of wood. It shows that he freezes water and it actually can stick to things. So we see a reaction that's getting colder and a reaction that's getting warmer. And that's what we're going to be talking about today, is how is that happening, and why is energy being transferred when bonds are being formed and being broken. So the first thing we're going to discuss is the chemical potential energy. Okay, that's the energy that is stored in bonds. So if I look here, here's a list of different types of bonds and the strength that's required to break them, or the energy that's released when they're formed. So if we look here, a hydrogen bond has 436 kilojoules per mole. Joules is a unit of energy, and moles is a counting measure. And if you look down, as the bonds become even a triple bond, you'll notice that it takes more energy to break triple and double bonds compared to single bonds. And you'll notice that there's a difference between, even within single bonds, there's different energy requirements for this, right? And we talked about this earlier in the year with Coulomb forces and such, but that relates. So this is more of a reference chart here that we're using to describe the energy required to break bonds, okay? Now, if we look at this example, okay, we have a reaction side and a product side. On the reaction side, we have two hydrogens and two iodine, and they're bonded together with themselves. And it requires energy to break these bonds. And then when they're broken, okay, that energy, when they reform, energy is re-released. So let me describe this concept with magnets. So if we have magnets, right, if I put energy in, they break. But if I put energy and they form new bonds, do you hear that clicking sound? That means energy, if you can think of it, energy is being released. So energy is released when bonds are formed. And it takes energy to break the bonds because there's no sound being made. It's like I have to take my breakfast this morning, fuel my muscles to pull this apart. It takes energy to break it apart. And when bonds are formed, they release that energy. So if you use this analogy to kind of comprehend what is happening, it'll start to make sense. So to break these bonds, I have to break them apart, and then they'll rearrange themselves and they'll form new bonds, okay? And now you're forming hydrogen iodide. Now, the law of conservation of energy, in a chemical reaction, energy is neither created nor destroyed. This is similar to the law of conservation of mass, which we talked about in our previous video, which we discussed how matter is not created or destroyed, and its atoms are simply shifted around. The same thing goes with energy. This energy that's put into these bonds is the same energy that's released if we make the same bond. But if you look here, the bonds that are being broken and the bonds that are being formed are different. They're not the same. So there's going to be a difference. So energy's got to come from somewhere, or it's being made in the reaction and put into the surroundings, or it's being taken from the surroundings, okay? And this first definition is when bonds are forming, it's exothermic. If heat is released, it will be absorbed by the surroundings and feel warmer. So for example, when we had this supersaturated solution that we made, Okay, what happened is when it became a solid, what was happening? All those bonds were being formed, and it was falling out. It was falling out of solution and becoming a solid. Basically, all that was happening was bonds were forming, and it was releasing a great deal of heat. Okay. On the next example, we have bonds breaking that are endothermic. If heat is absorbed, it will be taken by the surroundings and feel cooler. So when we mix ammonium nitrate and barium hydroxide, these two solids, and we shake them together to create that reaction, what was happening is more bonds were breaking than forming. The products were had a different potential. So what was happening is there was more of this going on, and it was absorbing that energy from the surroundings, and it was getting colder. Okay, so right down here, this is the two graphs that I need you to be familiar with. Okay, in your notes, really all you need to do, this has a lot of information. All I really want you to do is follow a simple trend. If you see this chart that's representing energy, right, and you have this reactants and we have products, and if it's going down, it's releasing energy. And that means if it's releasing energy, it's heating the surroundings and it's causing the surroundings to become warmer, right? That's an exothermic reaction. If our reactants are underneath our products, it goes up like this, it's now absorbing energy, and it's an endothermic reaction. All right, so all I need you to know is that there's this graph, we have reactants and products, and if it's going up, it's endothermic. If it's going down, it's endothermic. And if you notice from our example above, okay, if we notice it took 500, if we combine the energy required to break the H2 bonds and the iodine bonds, it's going to equal 587 kilojoules. But at the same time, bonds are being formed, and it's releasing 594, which is a little greater than this number. So overall, is it going to get cooler or warmer? It's going to get actually a little warmer. And if you look down here at our example, it's a -7. It's going to come down, and it's going to release that energy. Okay? All right. And let's talk a little bit how these reactions occur. So collision theory states that bonds are broken when molecules collide with enough energy. Okay? So what's happening is, in our example from the previous video, we talked about the conservation of mass. We talked about how we basically blew up a hydrogen and oxygen balloon. It was filled with these two gases. They weren't reacting with each other. There wasn't enough energy because you got to think about it. These molecules are moving. All the atoms are moving. They're vibrating. And when we add energy, what happens? They vibrate faster. They move quicker. And because they can move faster, they bump into each other and they collide, and then it breaks those bonds. It needs energy to break bonds. And when we put a flame underneath our balloon, it had just enough energy to cause these bonds to break and then reform into new products. Okay? And the reaction rate is the speed at which reactants become products. Okay, it's how quickly the reaction occurs. When we think about rust, it takes a very long time for rust to form, while blowing up oxygen and hydrogen, it happens very quickly. Okay, one of the things that affect reaction rates is the temperature. If the temperature is lower, there'll be less, these molecules will be moving slower and they'll collide, and only a couple will actually hit that enough energy to break the bond. But when we increase the temperature, they're moving faster. Do you notice how they're moving quicker? And they'll be bumping into each other and breaking those bonds and to form new bonds much more quickly. Okay. All right, and here's that balanced equation of hydrogen and oxygen forming water. Now, let's use another diagram of energy to show this phenomenon. I like this picture. This really summarizes everything I've just been discussing. So if we look here, we have a hydrogen-hydrogen, hydrogen-hydrogen, and an oxygen bond. So there's 3 bonds that are being formed, okay? And it takes energy to break these bonds, okay? So if we imagine energy comes in and breaks these bonds, okay? They're separated, okay? And now they're forming H, 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 and O, O. Do you see how they're all separated? They're not together anymore. Well, now they're going to recombine. And when they recombine, they release that energy. And it happens to be that there's more, it actually, when the bonds form, there's more energy being released than there was it required to break. That's why hydrogen and oxygen reacting is very exothermic, okay? And it brings those bonds down, and it shows that there's an H2O molecule and an H2O molecule. And if you notice, there's 3 bonds, 1, 2, 3. And if you look over here, there's 1, 2, 3, 4. There's actually more bonds now being formed than there was being broken. So it definitely will most likely be exothermic based on this scenario. Okay, and take some time and appreciate this diagram because it shows you, okay, it's a lot like the diagram above, right? Because up here, bonds are being broken, and then we're flipping over and bonds are being formed, okay? And they're releasing that energy, okay? So it's a balancing act. It's just a matter of knowing what side of the equation is going to have a greater effect. And in this circumstance, the formation of the products has a greater effect, so it's going to be releasing energy and making the system, the surroundings warmer. So just remember, when bonds are forming, they release energy, and when they break, they're absorbing energy from the surroundings, making the surroundings cooler, while the ones that are forming is putting energy into the surroundings, making them feel warmer, okay? If you have any questions, come see me. We took a quiz today. Come swing by my class, and I'll have you take that on your own time, okay? Thanks for watching.